In this video, we're going to introduce Faraday's law. So to start with, let us just state Faraday's law and then go through all of the pieces of it and try to make sense of what it means. So Faraday's law says that the EMF, which is also known as the electromotive force, is equal to the negative of n, where n is the number of loops, and we'll get to what that means, multiplied by the derivative of the magnetic flux with respect to time. Okay, so let's begin with the thing that we have seen before, which is the magnetic flux. In a previous video, we talked about how the magnetic flux is given by either the integral of the magnetic field dotted with dA, or in the case of a spatially uniform magnetic field, that is a magnetic field that has the same direction and magnitude everywhere in space, we can write that the flux is simply B dotted with A, where A is the area vector. And we can write this as the magnitude of B multiplied by the magnitude of A multiplied by the cosine of the angle between those two vectors. As a quick reminder, let's just look at an example of where we could calculate the magnetic flux. So imagine that we have some loop here in a uniform magnetic field. Well, the magnetic field is the same strength and points in the same direction everywhere, which indicates that we can use our shorter equation, just B dot A, to calculate the magnetic flux through this loop. In order to calculate magnetic flux, we always need an area, and that area is the area enclosed by our loop here. And remember that the area vector here always has a direction perpendicular to the surface area enclosed by the loop. So this loop is lying in the plane of the board, which means that we have two possible area vector directions. The area vector can point out of the board, or the area vector can point into the board. Since the magnetic field is pointing into the board, we'll pick the area vector to also point into the board so that our flux is positive in the end. Okay, well, so quickly what we could do to calculate the flux here is we can use our shorthand here. Because my magnetic field vector and my area vector point into the board, the angle between those two vectors is 0, and the cosine of 0 is 1. So our flux in this case would just be whatever the magnetic field is multiplied by the area. Another note that we should make is that we are being very specific about the magnetic field being an external magnetic field, not a magnetic field generated by this loop. So in this video, we're going to be very careful about the two types of magnetic fields that we're interested in. Either we're going to be interested in external magnetic fields that are created by some other source and create a flux through our loop. We're also going to be interested in currents flowing in our loop generating their own magnetic fields. We will call those induced magnetic fields, and we'll get into what that means in a minute. Next, let's turn to our variable n. N simply refers to the number of loops. So here I have some copper wire in a loop. It could look like this loop. N is simply the number of turns in this loop. So here I have maybe 20 turns of wire. So N in this case would be 20. The more turns you have, the more EMF you will generate, because our EMF scales linearly with the number of turns of our loop. Finally, let's turn our attention to the electromotive force, or EMF. So the EMF is in fact not a force. It acts like a voltage or a battery in the circuit, in that it drives current around the circuit. And we actually can use EMF as a voltage within Ohm's law. So we can say that the EMF is equal to the current multiplied by the resistance of a loop. And we could use this, for example, to calculate the current flowing in the loop for a given value of the EMF. Now, EMF is not technically a voltage in that it does not obey all of the rules that we have for voltages. Particularly, it does not obey the Kirchhoff loop rule, where the total change in voltage around a closed circuit should be 0. That will not be the case for EMF. And this is why we have a different symbol and terminology for electromotive forces than we do for voltages, which follow Kirchhoff's laws. Now let's consider a specific example of calculating the EMF for a known loop and magnetic field. So imagine that I have this same loop here where I've now given it a known radius of 0.5 meters inside of an external magnetic field pointing into the board. Now, if we want to find the EMF, what we are interested in is how the flux changes. So in this case, the flux is going to change by changing the external magnetic field. So let's assume that we have an initial external magnetic field that points into the board with a magnitude of 1 millitesla. And then that magnetic field is removed over the course of 2 seconds. So we begin and we have a magnetic field into the board of 1 millitesla, and we end with 0 external magnetic field. Okay, so what that means is that we can actually calculate the initial and final flux. We have an initial magnetic field multiplied by area. We have a final magnetic field multiplied by area. So the initial flux is given by B initial times A initial, which is our magnetic field multiplied by our area vector. It's a dot product, but because both vectors point in the negative z hat direction, it turns out just to be the multiplication of the magnitudes of these two vectors, and that leads to this result. We can also calculate the final magnetic flux due to our external magnetic field. Well, because there is no final external magnetic field, our final flux is 0. From this, we can calculate our change in flux, which is this value here, negative 25 pi times 10 to the negative 7th Tesla meters squared, because the flux has units of magnetic field multiplied by area, Tesla meters squared. Okay, so now we know how much our flux changed, and we know the time over which our flux changed. So we are now ready for our final step, which is to calculate the EMF. Now, for right now, we're going to ignore this minus sign. The minus sign ends up giving us information about the direction that current would flow within our loop. But for right now, we are simply going to be calculating some magnitudes, or this magnitude of the EMF, and we're going to ignore that minus sign at the moment. So we can now take our number of loops and multiply it by the time derivative of our magnetic flux. But in this case, because our magnetic field changes at a constant rate from some known initial value to some known final value, we can actually replace our derivative with just the change in flux over the change in time. This being said, we can now simply sub in our change in flux, which we calculated, our change in time, which we know, to find the total EMF, or electromotive force, of this example to be 62.5 times pi. Remember, the pi is coming from our area here, times 10 to the negative 7th volts. EMF acts like a voltage and in fact has units of volts. As a final piece of this example, we can now use our EMF to find the current that would flow through the loop during this change in flux. So if our loop has a resistance of 10 ohms, we can use our equation current equals EMF over R, which is just an Ohm's law equation where we replaced voltage with EMF. So we get our EMF divided by 10 ohms, which leads to 6.25 times 10 to the negative 7th amps as the current that would flow through the loop during this time when the magnetic field is changing. Now let's look at another example of calculating the EMF for a given situation. So the example that we're going to look at now is a loop in a magnetic field. The magnetic field is once again uniform and pointing into the board. But this time what's going to happen is we're going to allow our loop to actually expand. So imagine if you have some loop and you simply stretch it out while keeping it in the shape of a circle. When we do this, the area of our loop is going to expand. Since the flux depends on both the magnetic field and the area, our flux is therefore going to increase. Okay, so to begin with, let's write down the magnetic field here. So in this case, we're going to say that the magnetic field is 2 millitesla in the negative z-hat direction into the board. Okay, our loop is expanding, which means that the radius of the loop changes with time. So now we're going to write our radius as a constant. So this is like our initial radius, 0.2 meters. And then it is going to expand at this rate here. So it's going to be 0.2 meters, our initial loop radius, plus 0.04 multiplied by t. So as time increases, our radius is going to be increasing at a linear rate. Okay, since we know our radius, we can therefore write our area. So the area is pi r squared. Inserting our r value into this equation, we simply have pi times our radius equation squared. And this is all in the negative z-hat direction. Again, because our loop is in the plane of the board, we could choose the area vector to either be out of the board or into the board, and we simply choose the one that is in the direction of the magnetic field to avoid an extra minus sign. In this example, we're simply going to be calculating the magnitude of the EMF anyway, so it really doesn't matter which direction we choose our our area vector to point in. Okay, now we can write down our magnetic flux as the dot product of the area vector and the magnetic field vector. Since they both point in the negative z-hat direction, this is simply the product of their magnitudes. So we have the area vector multiplied by the magnetic field, where we've switched the units from millitesla to normal tesla. Now we need to take the derivative of the flux, because the EMF depends on the derivative with respect to time of the flux. You can clearly see that our flux depends explicitly on time, so we can simply take this derivative. We can pull the 2 times 10 to the negative 3 and the pi out front, since those are constants, and then taking the derivative of this term using the chain rule, we get 2 multiplied by the term in parentheses here, and multiplied by 0.04, which is the derivative alone of 0.04 times t. Now we have an expression for the derivative of the flux with respect to time. Now, we can find our EMF here by multiplying the number of loops by our changing flux, or our derivative of flux with respect to time. Assuming that we only have one loop here, so n equals 1, we find that the EMF is equal to this expression here, which I've simply copied over from this bottom line here, while I've combined a few of the other constants into the term out front. Now, if we want to find the EMF at a specific moment in time, we simply need to assign a time that we're interested in. So for example, if we wanted to find the EMF at t equals 0 here, we simply set t equal to 0 in our equation, and we find this as the magnitude of our EMF at that time. We could choose any other time that we want, plug it in here, and find the EMF at that moment as well.